I'm Marissa Encarnacion, a senior mechanical engineering student, and I'm also the president of Gonzaga Robosub.
Hi, I'm Blaine. I'm an incoming junior and the electrical team lead.
Hi, I'm Aaron Weber. I'm a incoming senior electrical engineer and I lead the mission computer team.
What's up guys, my name is Brandon Takahashi. I'm an incoming senior and currently the lead of the embedded systems team.
What's up everybody, my name is Kevin Matapali. I'm a graduate and part of the embedded systems team.
My name is Alec Wilson. I am a senior studying electrical engineering.
I'm Alexander Delgado and I'm a mechanical engineering student on the Robosub team.
Say that Gonzaga Robosub really focuses on the education of all their members, and we really strive to provide each member with an extracurricular experience that they could not attain inside the classroom.
The electrical team is in charge of power distribution, battery management, sensor connection, and this year has been hard at work developing a hydrophone system for our submarine.
The embedded systems team focuses on providing an interface between our mission computer and our motors and sensors through serial communication using the Texas Instruments microcontroller. Whenever a new component is added to our sub, we help integrate it.
The mission computer team works on the brain of the sub, which takes the data from the embedded system and the camera and uses that information to determine what it needs to do to complete its tasks. Additionally, we work on the mission control platform, which is a platform that testers can use to manually control a sub and read sensor output. Our tasks we've been working on at the moment have been RFID tags to start preset missions and working on a new version of our mission control platform.
The mechanical team works on all of the exterior components of the sub, so for example, the frame and the hull, and the mechanical team also works on how the sub moves underwater, so that would be waterproofing and thrusters and all those things. On our team, we do a lot of 3D printing, so all of our members, and we had about 6 to 7 dedicated members this year, all of our members learn how to use SolidWorks and learn how to 3D print in order to contribute to the sub. Two of the biggest projects on the mechanical team this year was rust and corrosion prevention, so making sure that the aluminum frame and other aluminum parts didn't rust in the water, as well as there was a large project, a large group of people working on the torpedo launcher, or at least designing one. It was in the prototyping phase all the way up until the point where school was closed. The 2020 sub is called Terrapene, which is the scientific name for a box turtle, and this really speaks to the sub's box-like hull or rectangular hull, which makes it really easy to access components and to seal the sub. However, it's not very hydrodynamic, but in our case that's not really super important, or at least drag is not super important because we're not moving at high enough velocities. The frame design consists of 2 aluminum side panels held together by 80-20 aluminum, and the side panels have a very particular hole pattern drilled into them, and this hole pattern allows us to be able to attach any component to the side that we want in whatever configuration we deem necessary.
So for our mission computer, we're using the NVIDIA Jetson. Its low power design allows us to have a lot of performance in a small package. It's also very useful for our machine learning development, which we're currently working on. To maintain communication between the Jetson and our motors and sensors, we're using the Texas Instruments TM4C microcontroller. This microcontroller allows us to communicate serially between the motors and sensors and provide an interface with low power design as well. As far as powering our sub, we have 3 15-volt batteries in parallel. In some of our past models, we've had some issues with hull leakage, so this year we implemented a custom water leak sensor to detect if any water has gotten into the hull before it's too late.
2 critical platforms which run code for our system involve the mission control and the embedded systems platforms. Code running on our microcontroller is written in C++ and utilizes the TivaWare libraries provided by Texas Instruments. Our mission control platform involves our user interface, which utilizes C# on the front end while using Java on the back end. We also have a machine learning team which is currently using Python and OpenCV for future developments.
Our strategy going into this year was to increase the reliability of tasks that we could already perform last year, while simultaneously adding new functionality to allow us to perform new tasks this year. Last year we were pretty much limited to the gate and the coin toss, and unfortunately this year got cut short before we were able to get confident in too much more than that. However, we do have some big plans in the works for as soon as we can get back to development.
For the gate test, we're about 80% confident on being able to make it through, as we do still have some slight gyro drift issues going to one side or the other that we weren't able to quite iron out in the time we had the test, but it's fairly consistent. For the coin toss, assuming we don't have that issue, we're about 95% confident on being able to succeed at that, as we've tested it several times, and our sub usually orients towards the gate with little issue.
We determined that hydrophones would add the most new functionality to our sub, as they would allow us to attempt two new tasks: the torpedo task and surfacing in the octagon. The torpedo task would give our mechanical team something to work on, while surfacing in the octagon could be accomplished exclusively with good hydrophones and an accompanying algorithm.
In addition to the hydrophones, we've also been working on improving our image recognition technology. Our immediate plan for that is to work on succeeding at the buoy task, but we hope it will be useful in helping us complete other tasks in the future. Additionally, we plan to use it as an extra level of security when going for the gate, instead of relying purely on holding a heading.
As part of the mechanical team, this year we decided to tackle a new obstacle in the competition: shooting a torpedo through the appropriate openings in order to score more points. To complete this task, a new mechanism had to be designed and built: a torpedo launcher. Due to the COVID-19 situation, the launcher never came to fruition, but several iterations of the initial design were created. In its current configuration, the launcher is spring-loaded with a revolver-style locking mechanism actuated by an electric motor. The whole launcher was to be 3D printed, and the plan was to have two of these on the sub.
The hydrophone system was developed in order to allow Terrapin to triangulate the location of a pinger and then head towards that location and surface. What makes Gonzaga Robosub's hydrophone system unique is that the hydrophones were made in-house as opposed to bought. The hydrophone system uses 4 hydrophones, each that have been confirmed to be working by using a waterproof Bluetooth speaker. However, this waterproof Bluetooth speaker cannot produce the high frequencies that will be used at competition, which is why we were developing a waterproof casing for a high frequency speaker that we had bought. However, development of this stopped due to COVID. Each hydrophone produces a relatively weak signal on their own, which is why we developed an amplification system. We decided to use an LM386 integrated circuit due to how common they are, as well as that it met all of our specifications. Due to it being extremely common, if we ran into any difficulties, there was a lot of resources online that could help us troubleshoot the problem. We set up each LM386 integrated circuit in the 200 gain configuration. When tested in the pool with the hydrophones hooked up, we saw a gain of 500 volts over volts. We were working on before COVID shut down development of the filtration system. We were deciding between using an integrated circuit or a Fourier transform. We're leaning towards going with a Fourier transform since it is software based. This means it's cheaper and it is more configurable.
So to test new components before we integrate them onto the sub, we developed a miniature robotic car, aka the Minibot, which we use to test new electronics before we put them onto the sub. The Minibot adapts our programming environment from the sub to a land vehicle, so that allows us to debug and test more efficient than before. We also do a lot of PID testing on the system as well, so that means that we don't have to pull test until absolutely necessary, saving time for us and for the other teams working on the sub as well. This car is also a great platform for new team members joining the embedded systems team to become familiar with our system before working on the sub. During the COVID-19 pandemic, the embedded systems team has continued development on the code and as well as integrating new electronics because we've been able to use the Minibot. We have one person using the Minibot at their house and the rest are using Git repositories and Zoom meetings to help contribute to the code. This allows us to continue testing as well as become prepared for when things come back to normal. We can start integrating new things faster than before.